Hi everyone, this video covers the rest of the 4A notes and the 4B notes. Let's get started. So, problem F is f of x equals x squared minus 4 over x plus 2. If you factor this, you have x plus 2, x minus 2 on top, x plus 2 on the bottom. So, for the horizontal asymptote, the degree of the top is bigger than the degree of the bottom, so there is no horizontal asymptote. The x plus 2, these cancel out, so that's going to be a hole. So there's a hole at negative 2. And if you cancel out the x plus 2's, and then you plug negative 2 in here, you end up with negative 4. So there is a hole at negative 2, negative 4. And because these cancel out, there is no vertical asymptote. The graph of this is going to look pretty much just like x minus 2, except that there will be a hole right here. So the domain and range are going to be everything excluding the hole. There's going to be an x-intercept at 2, 0. And we know that because if you set this equal to 0, you get x equals 2. All right, problem G. Let me blurry here. We have f of x equals x squared minus 2x minus 3, 3x minus 3. So the top factors to x minus 3, x plus 1. The bottom factors to 3x minus 1. So as you can see, nothing actually cancels out, although these are pretty close, so don't get confused by that. The horizontal asymptote, the degree of the numerator is bigger than the degree of the denominator, so there is none. There's a vertical asymptote at x equals 1. And there are no holes because there's no common factors on top and bottom. Now, one thing you could notice in this case, the degree of the numerator is 1 higher than the degree of the denominator, so there is a slant asymptote going on here. And you would find this using synthetic division. So, let's see here. If we're dividing by this, if you set this equal to 0 and solve for x, you're going to get x equals 1. So we put 1 in the box, put the coefficients in here, synthetic division, y equals x minus 1, that's going to be our slant asymptote, because negative 4 is the remainder. So there's a vertical asymptote here, there's a slant asymptote along the line y equals x minus 1. Okay? And the domain is everything except the vertical asymptote. The range is everything because there is no horizontal asymptote and no holes. And there are 2 x-intercepts at negative 1 and at 3. All right, and finally, problem H. We have f of x equals negative 3x squared plus 12x minus 9 over x squared minus 5x plus 4. The numerator factors to this, the denominator factors to this. Looks like we have a hole at x equals 1, a vertical asymptote at x equals 4, and a 0 at x equals 3. So the horizontal asymptote is y equals negative 3, the vertical asymptote is y equals 4. Again, there's a hole at 1, and if you plug that in, if you plug 1 in here, after canceling out the x minus 1, you'll get negative 2. So the hole is at 1, negative 2. The domain and range, the domain is everything excluding the vertical asymptote and the hole. The range is everything excluding the horizontal asymptote and the hole. And then, of course, as we said before, the x-intercept is at 3. So the graph will look something like this. Vertical asymptote, horizontal asymptote, the hole, the x-intercept. And because it's negative, we know it's flipped over the x-axis. All right, let's get into the next section. 4B, arithmetic and geometric sequences. Let me zoom in a little bit. Okay, let's start with some definitions. An arithmetic sequence is a sequence A sub n is an arithmetic sequence if it can be written in the form a naught plus d, a naught plus 2d, dot, 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 a naught plus d, n. For some constant d is not equal to 0. So what's going on here is each term of the sequence, you're adding the same thing. You're adding it once here, you're adding it twice here, and so on. So like 2, 4, 6, 8, 10, 12, because you're adding 2 every time, that would be an arithmetic sequence. The number a0 is the initial term, and the non-zero number d is the common difference, or constant rate of change. Common difference seems to be the more the term used more frequently, but I wanted to throw this in there just in case that appears on the AP exam. Constant rate of change, same thing. Each term in an arithmetic sequence can be obtained recursively from its preceding term by adding d. So recursively and explicitly defined sequences, these are terms you're going to see a lot. A recursively defined sequence is a formula you can use to find the next term of a sequence. So if you're looking for some term in your sequence, and you know the sequence is arithmetic, you can take the previous term and add the common difference, and that will give you the next term. And this is where n is greater than 0, n is a whole number. Okay, let's see here. The explicitly defined sequence, this is a sequence where if I want, say, the 10th term of the sequence, I can plug in 10 for n, and then of course also plug in your initial term and the common difference, and if I do that, I will get this. Alright, same idea with the geometric sequence. A sequence a sub n is a geometric sequence if it can be written in this form. In this case, we have our initial term, and we are multiplying each subsequent term by something. So this would be like 2, 4, 8, 16, 32, 64, 128. What I'm doing is I'm multiplying by 2 every time. Okay? And this would be the explicitly defined sequence. If I'm plugging in if I want to know the 8th term of a sequence, I would plug in 8 for n, and then also plug in the common ratio and the initial value, or the initial term, and that would give me the 8th term. This is the recursively defined sequence. So if you want to know a particular term of the sequence, you can take the previous term, multiply it by your common ratio, and that gives you the next term. So, the number a0 is the initial term, the number r is the common ratio, or constant proportional change. Each term in a geometric sequence can be obtained recursively by its preceding term by multiplying by r. Alright, so the big things you want to remember from this lovely set of definitions are the stuff in pink boxes. Okay? You'll notice that here and here I drew a sub n equals. That's because frequently when you're talking about recursively defined sequences, it'll say a sub n equals a0 plus dn, or a sub n equals a0 plus r to the n power. So I wanted to add that in there. Alright, let's do an example. Example number 1. For each of the following arithmetic sequences, find the common difference, a sub n, a recursive rule for the nth term, and an explicit rule for the nth term. Alright, so our first sequence, we have -6, -2, 2, 6, and 10. It looks like we're adding 4 each time. Pull out another thing here. My other thing has disappeared. That's all right. Okay, I might be showing the answer here. Okay, so the common difference is 4. The initial term is -6. And this is explicit form and this is recursive form. The recursive rule, we have a sub n equals a sub n minus 1 plus 4. I'm following this here. Oh, sorry. This one here. Pointed to the wrong one. A sub n equals a sub n minus 1 plus d. The recursive rule. The explicit rule, we've got a sub n equals -6 plus 4n. This one, I'm following this here. So the initial term plus d times n. So -6 plus 4n, and this is for integers n greater than 0, or you can say n's a whole number. So then it says use this to find a sub 10. So basically that means you're going to plug in 10 for n. When you do that, you get 34. So the 10th term is 34. Or the 11th term, because A0 is the first term. Okay, same thing here. This time we're adding 2p each time, so our common difference is 2p. For the recursive rule, I'm going to be using this formula, plugging in d. So my initial term is negative 2p. My recursive rule is a sub n equals a sub n minus 1 plus 2p for integers n greater than 0. The explicit rule, I'm following this one. So negative 2p plus 2pn. You could also write it like this if you wanted to give factored form, and this is for integers n greater than 0. So when we plug in 10, we get 18p. All right, practice problem number 1. For the arithmetic sequence 6, 10, 14, 18, find the common difference, a sub 10, a recursive rule for the mth term, and an explicit rule for the nth term. So same thing as last time. It looks like we're adding 4 each time, so the common difference is 4. I didn't rewrite the rules, but if it helps you, you could rewrite the rules over here. The initial term is 6. A sub n is a sub n minus 1 plus 4, because 4 is your common difference. This is the recursive rule. The explicit rule, a sub n equals 6 plus 4n. This is the explicit rule, and when you plug in 10, you get 46. All right, let's take a look at some geometric sequences. For each of the following geometric sequences, find the common ratio, a sub 10, a recursive rule for the nth term, and an explicit rule for the nth term. All right, so for A, we are clearly multiplying by 2 each time. So that means the common ratio is 2. I'm going to be using these two rules again. I'm going to find the recursive rule first. So the initial term is 3, a sub n is 2, a sub n minus 1. And notice that because it's multiplying, the coefficient goes out in front. This is the recursive rule. A sub n equals 3 times 2 to the n power, because 3 is the initial term and the common ratio is 2. If you plug in 10, you get 3070. This is also a geometric sequence. Each time we are multiplying by 10 to the second power, or you could also say multiplying by 100. So r is 10 squared, or 100. The initial value is 10 to the negative third power. A sub n equals 10 squared times a sub n minus 1. This is the recursive rule. The explicit rule is a sub n equals 10 to the 2n minus 3. This is the explicit rule. And when you plug in 10, sorry, it's smeared a little bit. 2 times 10 minus 3 is 17. So 10 to the 17th power, and I left it as an exponent. Practice problem number 2 for the geometric sequence, same thing. This time we're multiplying by 3, and we're finding a sub 7. So the common ratio is 3. Plug everything into the same formula. Let me write out recursive and explicit. I meant to do that. And then when you plug in 7, you get 4,374. All right, exploration. Your challenge is to find the sum of the natural numbers, numbers from 1 to 100 without a calculator. So this is how you might do this. Imagine writing the sum 1 plus 2 plus 3 all the way to 100 on a wide piece of paper. Underneath its sum, imagine you write the sum 100 plus 99 plus 98, and so on. If you add the numbers 2 by 2 in vertical columns, you would get an identical sum 100 times. So here's what's going on. You have 1, 2, 3, all the way to 100, and here we have 100, 99, 98, 1. If you add vertically, you're getting 101 plus 101 plus 101 plus 101. You're getting 101 added 100 times. So the sum of 100 of the 100 identical numbers would be 10,100, because 101 times 100 would be that. Explain why half the answer in part 2 is the answer to the challenge. Can you find it without a calculator? The sum involves 2 copies of the same progression. So if we just wanted to add 1 through 100, it would be half of this, because here we have added 1 through 100 twice. So if you take this, divide that by 2, you get 5,050. Alright, some more definitions. The sum of a finite arithmetic sequence. Let these be a finite arithmetic sequence with common difference d. Then the sum of the terms of the sequence is the sum of a sub k from k equals 0 to n. And this is how it's read. The sum of a sub k from k equals 0 to n. This is called a sigma. The k equals 0 is called your index. So if you have some sum and you want to find what that sum is, you could use this formula. This would, or this one. Either one works. The sum of a finite geometric series. Let the a's be a finite geometric series with common ratio r not equal to 1. Then the sum of the terms of the sequence is this. So the sum of a sub k from k equals 0 to n, once again, you're adding all these together, but you would use this formula. And again, this is sigma, and this is your index. An infinite series is an expression of this form. So this is when the series doesn't have an end. It continues on to infinity. Sometimes you can find that sum, and sometimes you can't. Oh, and I said that here. Sometimes a sequence of partial sums, all of which are true sums, approaches a finite limit s. In this case, we say the series converges to s and it makes sense to define s as the sum of the infinite series in sigma notation, blah, 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 blah. What this means is that sometimes, even if it's an infinite series, because the numbers are approaching some value, you can actually find that sum. Sometimes you can't. Sometimes the numbers continue to get bigger, or it oscillates between 2 values or something like that. If the limit of partial sums does not exist, then the series diverges and has no sum. Alright, let's do some examples. Example number 3. A corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? Okay, now in this case, the numbers are small enough where you could probably just think about it and solve this just using basic arithmetic, but I'm going to use the procedures we just learned. So our initial value is 8. That's the front row. Excuse me. And the final value, the top row, is 24. And it says the common difference is 2 because it increases by 2 with each row. So using that information, we can come up with an explicit formula. A sub n equals a naught plus nd. That's the formula for an explicit rule. I'm going to plug in these values. This gives me 24 equals 8 plus 2n. Solve for n, and we find out that n equals 8. So I'm using this formula. The reason I'm using this formula from the previous page is because I have a naught and a n. And now I also have n. So I plug everything in, I get 144. All right, practice problem number 3. The first row of seating in section J of the Athena Arena has 7 seats. In all, there are 25 rows in section J, in each row containing 2 more seats than the row preceding it. How many seats are in section J? So this is a very similar thing to what we did in the previous problem. The only difference is they're telling us write out how many rows of seats there are. but they're not telling us how many are in the top section. So we're given the initial value is 7. We're given the common difference, that's 2, and we know that the 25th row would be a sub 24, but we don't know what that is. Notice it's 24 and not 25 because the first row is 0. So the 25th row would be 1 less than 25. So a sub n, using the explicit rule again, I'm plugging a sub a naught in for, 7 in for a naught. We know d is 2, so it's plus 2n. And in this case, we know that n is 24. So I'm going to plug everything in, I get 55. So now I'm going to use this formula again. 24 plus 1, 7 plus 55 divided by 2, and I get 775. All right, sorry for the smear there. Find the sum of the geometric sequence, blah, 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 blah. Okay, so same thing here. We're multiplying by negative 1/4 each time. So my initial value is negative 1, and my common ratio is negative 1/4. Plug everything in to solve for n. We're going to get n equals 10. Okay. So from... Let me go back and explain why n equals 10. It's because we're given the last term. So this is the last term, so n has to be 10. Okay, so then we plug everything into the common ratio. This is the formula on that other page. I'm going to plug everything in. Notice it's an n plus 1, so this becomes an 11. And I get negative, this is rounded, there is a number after the 0, negative 0.800, and I forget what comes after that. All right, practice problem number 4. Find the geometric sequence 6, 3, 6, 12, all the way up to 12,288. Same thing. Put a box around this. We know the a naught is 3. The common ratio is 2. We're going to use this, and we find out that 3 times 2 to the n power. 2 to the n power is going to be 4,096. Hopefully you guys remember logs from Algebra 2. In order to get rid of this 2, you need to take log sub 2 of both sides, and so n is going to equal 12. So now we know that this top number is 12. Plug everything in. A sub k equals this. Plug everything in, and we get 12,573. And finally, exit ticket. Alright, so I wanted to do just a few problems where we're actually adding all the numbers together, just so you can kind of see. We used the formulas before, and when you have large values or a lot of numbers in a sequence, the formulas are the best way to go. But here I want to show you guys how to do it just one term at a time. So if we have k equals 1 all the way to 5, basically what you're doing is you're plugging in 1, plugging in 2, plugging in 3, then 4, then 5, and then adding all those terms together. That's what this sigma means. You're finding the sum of all these terms. If you do that, you get 45. Down here, we've got 0 to 12, cosine of n pi. So if we plug in 0, we get 0, then pi, 2 pi, all the way up to 12 pi. Okay? Cosine of 0... Cosine of 0 is 1, cosine of pi is negative 1, then negative 1, then 1, then negative 1, then 1, then negative 1. It kind of, like, it repeats. Okay? So, we've got from 0 all the way to 12. I didn't label this one. Hold on. Here we go. Most of them cancel out, and we're left with 1. Okay, and we have one infinite series. We have 1 to infinity, 3 over 10 to the k power. So this is 3 over 10, plus 3 over 100, plus 3 over 1,000, and so on. It's a little easier to see this one if you write them in decimal form. 3/10 is 0.3, 3/100 is 0.03, 3 over 1,000 is 0.003, and if you add all these together, you're going to get 0.3 repeating, which is 1/3. All right, and that's the end of this section. Thank you so much for watching.